In order to get to the second fundamental theorem of calculus, we have to take a side step here and take a look at viewing a definite integral as a function. Now, I've been very clear about definite integrals giving you a value, but we can manipulate them to do something else. So let's say we take the function capital F of x to be the integral from a to x of f of t dt. So the big difference here now is we have a variable in the limits of our integration. And so that's going to change everything. So instead of actually getting a value out of this, we're going to get a function. So to see that, let's take an example. So say f of t is just the function t, and we use a of 0. So then our capital F function would look like this. Integral from 0 to x, f of t dt, or in other words, integral 0 to x, t dt. Okay, so even though we can work that out, I want to show you what we're really talking about when we do this integral. We're saying that for any x value, the value of this function, capital F of x, is what we would get if we did 0 to that x value as an integral t dt. For example, let's say we wanted to evaluate capital F of 1. Well, there goes the 1 in there, and then in order to do this, this is the integral that we have. But that definite integral is the area under the curve, basically y equals t from 0 to 1. So that's this area right in here, from 0 to 1 under that curve. Then what would it mean to do 2? Well, we'd still be looking at the same curve, y equals t, but instead we'd be going 0 to 2 now. So we get all of this. And so on. If we did 3, now we go 0 to 3. So we would get this. So you see that we're basically, with each increment, we're adding more and more area from under the curve. So we started going 0 to 1, then we went 0 to 2, and 0 to 3, and we kept basically adding on area. So this is a way that we can actually use the definite integral to make a new function, where basically this type of function says whatever value x you want, you're going to find the area under this curve from some constant a to that variable, to the value of that variable. So now, if this thing is actually a new function, we should be able to take the derivative of it. And that's what we're going to do here in the second fundamental theorem of calculus. We're saying, let's say if little f is continuous on an open interval I containing this a, then for every x in the interval, okay, the derivative with respect to x of this integral function a to x of f of t dt actually comes out to just be f of x, the little f of x. Okay, a couple of things to notice here. This a had no effect. This a didn't matter because it doesn't come into anything with the end result. So it doesn't actually matter what constant we're starting at the bottom there. Then the other thing is, what did we really do? We essentially took f of t, we took the little function little f, we integrated it, and then took the derivative. So it's not surprising that basically we got back what we started with, because we did two operations that are pretty much the reverse. Integration and then differentiation. Now there are some subtle details in there that we're going to have to be careful about, But really, we did the opposite, and so we got back essentially what we started with. And the point of this theorem is really that we're not trying to do this as two steps. We're not looking to do this integral and then do this differentiation. We're looking to do it all at once. Just to show you that it really works in a sense, let me try and convince you that it's true. So what we're doing is taking the derivative of the integral a to x little f of t dt. Okay, well, imagine that we could integrate this integral inside, and imagine that it has that little f has an antiderivative capital F. Well, then we would have the derivative still outside. We would have capital F of t to be evaluated a to x, right? But that would be the derivative with respect to x. We would take f and evaluate it at x minus the evaluation at a. So we would get the derivative with respect to x of capital F of x minus the derivative with respect to x, capital F at a. Now, remember we said that the reason we used capital F here is because it's an antiderivative of f. Or in other words, if we take the derivative of capital F, we get little f. Well, that's what we're doing right here. So if we take the derivative of capital F, we get little f of x. All right? And then, sorry, that's the subtraction there. Then we're going to subtract the derivative of capital F at a. But capital F of a is just the function evaluated at a constant a. So this is a constant. Its derivative is 0. So we get little f of x. Okay? So we're saying that we want to be able to go directly from here to here without those steps in between. So another thing is that there really is a more general version here. The idea is that we don't need it simply to be x at the top there. Okay? So if we do the same thing, but we do the derivative with respect to x of the integral from a to some function u of x of f of t dt. Well, really we're just going to bring in the chain rule now. We're going to say, all right, well, if you want to take the derivative with respect to x of something, then you can really take the derivative with respect to u of this thing times du dx, right? So that's just the chain rule, which means now this, realize, is in u, and that's u. So that's like our original version. And that says basically, if we do the integral of f from a to u and then do derivative with respect to u, we should get back what we started with, except I get a change of variables and I put the u in for t, just like we essentially put the x in for t here. So we get f at u of x, and then we still need this chain rule factor du dx. All right, so we'll see how that comes into play, and then basically we can still do that in one step. We're essentially going to go from this right to this, but we'll have to see that in the examples.